take them, so,
Was it this one student we needed?
yeah, so, okay, I'll leave them out there, you can take them and keep them. I don't need them back, so.
Excellent. Okay, so the second lecture, and we'll continue with the experimental perspective on the electron-ion collider. And Kong is going to continue today with DIS. Steve.
Hey, thank you. And thank you for coming back. The second day. So today I'm going to continue my second lecture. So I will revisit a little bit about DIS. I think Vern yesterday gave a very nice talk about the DIS. A lot of the important things worth repeating. Okay, so there will be some overlap and some complementary views from my perspective. And then we'll move on to the EIC, the main meat. I call it the meat of the EIC physics, right? The three pillars. And then tomorrow I will go over a little bit of the reality check and some measure. So this is the DIS. You saw this diagram a lot. I remember yesterday we started from Rutherford scattering and then Moss scattering, with one angle. And then Vern actually complement this actual extra term about this, target mass corrections. And then you go into the Hofstadter that discovered that proton is not structureless, and then to select the DIS. So finally, DIS, you have an electron come in, photon in the leading order picture is a virtual photon hitting one of the quarks. So there are only two variables instead of one. So I wanted to make a point here is that this is important. We need two variables instead of one variable. Because in the Rutherford scattering or any of this elastic scattering, you can have this. Only one angle is needed. The entire problem is constrained by one angle. Of course, the photon carries some energies, but the theta and the energy of the scattered electron are correlated. However, if you can actually punch this proton through and break it, so-called inelastic scattering. So now the entire diagram, if I draw it very simply, exactly the same angle. Now, if you have an independent variable where the energy of the photon is different, then you can have a diagram where you produce a few particles, or you can have the same angle, it produces a lot of particles. So you see the difference is that one angle is not enough. It's not sufficient to describe the inelastic scattering. You need a second independent variable, which is, you can say the energy of the photon, or we can say momentum fraction, so-called XBJ. Okay? So this is actually a little bit tricky if you think about what an XBJ is. So I'm going to talk about this right now. So there are two variables now. One is angle, related is kind of the Q square, the resolution, and one is the sort of energy of this collision. So first one is the resolution. What does it mean? I kind of built this picture in your mind from yesterday is that the photon has a wavelength, right? The higher the frequency or the shorter this wavelength, you can actually resolve finer structure. So let me give you a pocket formula, right? 200 MeV, if you learn this, let's say high energy physics or particle physics, is about 1 Fermi. Okay, that's not to be precise, but 197. So that is about 1 Fermi. So if you keep increasing your Q square, your energies or your resolution, you're actually going to much finer scale in distance. And this is where the deep inelastic scattering, where the deep comes from. Okay. So that is the pocket formula you have to remember. I will quiz you. 1 Fermi, 200 MeV. Okay. And this 200 MeV is very important scale to our problem, to our QC. So this is actually very intuitive, right? Just the probe resolution. So now, can anyone tell me what is momentum fraction, right? So by definition, is the momentum carried by the quark of the entire proton. So if a proton has 10 quarks, so every quark has 1/10 of the momentum, right? It's kind of intuitive, but why do we need this sort of variable to do this? So one way to think about it is that Q square is a resolution in space, a spatial resolution, and XBJ is a time resolution, okay? So you may be confused where time comes in. Here is where time comes in. So here is a picture, okay? You probably have no idea what this picture looks like. This is a skier in the Winter Olympics, jumping off the hill, okay? You know the freestyle skiing? You go speed very fast, you jump, you flip, you turn around, you do all kinds of tricks. Hopefully you land without losing a bone or two. So now you are a reporter, but you're coming out of this 50s, it's very old technology. You have a camera, and your camera has a very slow shutter speed, okay? So this shutter speed means that you take a picture, the exposure time is very long, and then this is Alan Gould, is American skiers. It's jumping off. This thing happens so fast, your camera cannot resolve it because the time is so long. You just can see some kind of a structure, some object flying off the hill, but you cannot even tell if it's a human being. If it's a skier? What's the type of ski that she has? What brand that she's wearing? Okay, all these details is so blurry because your camera is so slow, you can't capture it. This is called a slow speed shot. It's a long exposure time. Okay? So now you go to the modern technology. You can take picture very, very fast, right? You take snapshot, very quickly. Now you can actually see the skiers, the color of the jackets, all the position that she was at. And this requires that your camera has a very fast shutter speed. So to summarize is that you can actually see things differently by dialing in different time resolution, right? It's a different time snapshot. You can have a very long exposure. You only see a structure, but with the fast speed camera, you can see the finer details. And this is exactly like the proton when we do DIS, okay? So here's how it goes. So now you're going with the proton in the lab frame, very slow. What you see is that you have seen 3 valence quark. Because the valence quark, the word valence is that it's a long time scale structure. It's almost always there. So now, even though you have a very long time scale, you still see this. It's just like this skier. You can still see an object flying down the hill. You can see the details. Now, what happens is when you go into higher speed, all of a sudden you start to see gluons come out. And that is the core physics of our field, right? When you accelerate the proton, you start to slow down the proton in terms of their time. So this is literally the relativity effect. So as an observer, the proton now goes faster and faster. The time dilation kicks in, right? So this is like changing this time resolution, this shutter speed. So now the gluon starts to show up. So the gluon is actually a short time scale presence. Only when you slow the proton down, you can see this fluctuation coming out. And now, if you're going even further, higher speed, these time dilations actually helps you, right? Because you are the observer, proton is going very fast, time dilation. All of a sudden, it's almost like an instant time snapshot that you're seeing that the gluons is actually there. So now what you can sensitive is to the gluons, not so much to the valence quark. And that XBJ or Q squared and X, this X, why is it so important? Because it relates to the energy scale and also the time scale that you're probing the proton. So it's not the physical reality changes, it's how you change your probe. So then you see different things. So eventually, if you're going to very, very high speed, you will see almost nothing but the gluons, right? The valence quark is still there, but you're not sensitive to them. You're overwhelming by these emerging gluons because you're going so fast in the time scale that you're seeing this overwhelming dominant gluon region. So actually, so I don't know if you can see the questions.
Just click OK. Click on this OK. It will disappear.
Okay. So one important question is, does it stop, right? So this is related to one of the questions for the electron-ion. Okay, I'll pause here. I want to ask any questions to this.
Yeah, I have a question.
Go ahead.
So, is it the best situation over here to be in a very, very high resolution? Because I see when you went to very high resolution, you don't see nothing but the gluons. Is that what you want?
If we wanted to study the structures of the proton in different kinematics. Yeah. So we not only want the high X or lower energy, we also want a high energy to low X. Yeah.
So you also care for the changes.
Yes, of course. And that is my next slide. Oops. Is that if you wanted to describe this in a quantitative way, we need this DGLAB. The DGLAB evolution is trying to, as exactly you said, how you understand this evolution, right? And of course, that you also have this so-called Parton distribution function. And I hope by now you have heard about this term. It's to describe the probability of finding a parton inside of the proton in a one-dimensional space. And then this interpretation is only in the leading order, DIS, right? A lot of caveat, but this is how you usually understand. For next to leading order, basically you cannot understand intuitive. Okay, I'm not going to talk about DGLAB or PDFs. There are many actually lectures later in the week we'll talk about it. But I want you to have this picture. Why we care about X and Q square. One is the spatial resolution, the wavelength of your photon, and the second is the energy scale or the time scale to see the different fluctuations. Okay, so now kinematics. So Bern actually showed very nicely yesterday the kinematics. So I will do a different way, but essentially the same thing, right? So this is the X and Q squared plane. So the really important formula. This is the formula that you should not Google about it. After today, you should memorize it, okay? Other formula, I don't remember either. But this one, I remember in my sleep, okay? Q squared equals to SXY. They're so important, okay? So that means that you have this X and Q squared plane, and it tells you the electron and proton, the kinematics. So let me show you. So this is an app written by my colleagues, Thomas Ulrich. And voila. So now we can do a quick experiment. So as I said, in the DIS problem, there are only two independent variables. Remember? Angle, energy. You can rewrite this variable however you want, but the information is there, only two independent. So you can say X and Y, or X and Q squared, Y and Q squared, energy of the scattered electron or quark. So it doesn't matter. So we usually do X and Q squared or Y and Q squared. And then you see that at Q squared equals to 1. And now X is 10 to the minus 2, okay? Or you can actually do 10 to the minus 1. So you see that here, the electron comes in. The line of this red line is the scatter electron. So it goes very forward, which is very confusing because in EPIC, in EIC, we call that backward. But forward right now means they maintain their momentum direction, okay? And then proton comes in. You have this so-called the current jet or the leading quark that you hit. And that quark goes also forward relative to the quark, to the proton, right? So now, resolution or Q squared, okay? The angle, how this is changing. So now you can see I'm going to increase the Q squared, okay? this is how x and q squared changes. So this is determined by the DIS kinematics, where you have a higher q square, you keep the same x, the formula that I want you to remember in your sleep. Q squared equals to S x y, right? So you increase the q square, the same energy, 18 on 275 collisions or square, and then you keep the same x, then you change basically the y when you change the q square. Okay? You can do it the other way around. But now you scatter electron goes much higher angle, and your quark also changes. Okay? So now you go to higher q square. You can keep changing, but it's, as Bern said, there's a regions that is all of a sudden it changes, right? So this is not always, you have to remember this picture. So now you can go 1 GeV q squared. You can go to different x. Okay, so this is x 10 to the minus 2. And then you can go to x 10 to the minus 3, x 10 to the minus 4. You see how different they are. Okay, so now this is the low x. Okay, now I'll quiz you. What's low x? Come, I just talk about x. What's low x stand for? Low momentum fraction. Good. What's the other way of saying it? What energy regime are we in? High energy. Okay. So now you think about the proton come in, and the quark actually gets almost backward, because the quark right now, or the whatever, the object, the proton you're hitting, that you actually have a very small momentum fraction. So with the same energies, it's very easy to knock this quark backwards, right? Because it doesn't carry so much momentum. If it's high x, lower energy, the quark carries more momentum. So that's why it tends to go forward. Now this quark has lower momentum, lower x. So then if you hit with the same photon, it can knock backwards. So that's why right now in low x, the quark actually bounce back. So in EIC, we call this is the backward region, because actually we should do it this way, okay? Or looking from the other side from the screen. That is our convention. But the idea is the same. The quark goes backwards, okay? So this is the DIS. You can download it from the app and play with it to get familiar with where the quarks and the electron goes. Okay. So now, after you have this idea about the DIS, so we have to be more specific on DIS. And then we have to go back to the structure, right? So for the structure function, I think yesterday, we now starting using sigma. And basically it was the solid angle, the energy, but also you can write it in terms of now the new variable, the dx dq square. Then you can have something like a mod scattering with something, right? For elastic scattering, that's where the form factor goes in, the elastic. Now it's a deep inelastic scattering. We're using so-called a structure function. So how do we understand the structure function? We usually write it in terms of so-called, there's a F2 and there's a FL, okay? So I wanted to give you an idea what's F2 and FL. So one thing that this is very important is that when you have a DIS process, this is a quark, this is a proton. The photon and the quark has to interact, and photon cannot interact with gluon directly, right? So now there's a picture that I want you to memorize, is that the photon actually has polarization. Okay. And then remember what we talked about, the quark. If quark is massless, when it's massless, the chirality has to be conserved. Right? So chirality at massless limit equals to helicity. And remember, helicity is the spin projection to the momentum direction. So if you just do a simple, you say, okay, the quark is massless, helicity has to be conserved. Imagine that the momentum, they are colliding in their center mass frame. And then I use a double arrow as their spin. So it's spin 1/2, either, whatever way you want. And the photon actually has two components. The photon has the transversely polarized and the longitudinally polarization. So that means photon is a boson, it's a spin 1 particle. So you can have S equals to 1, but then in the Z projection, you have SZ equals to plus minus 1, or SZ equals to 0. Okay. So this is called the transversely polarized, and this is called longitudinally polarization. So the photon has two polarization components. Maybe it's too low. Can you see it? Can you see the board? So now, the interesting happens right here. Now, when the photon colliding with the quark, now the photon needs to be absorbed by the quark. So this is before collision. After the collisions, the momentum changed direction. The quark get bounced back. Okay. So now the spin, nothing is making the spin to change. So the spin, in principle, will stay the same, right? But this created a huge problem. What's the problem? What? Chirality, helicity, right? Massless, they are the same concept. So now this is a right-handed particle, all of a sudden becomes a left-handed particle. And this is not allowed, right? So in order to make this happen, you need to compensate the spin. You need to flip the spin as well. So the spin from, let's say, minus 1/2 to positive 1/2, you need to have a spin component from your photon to compensate that. In other words, only the transversely polarized photon component can couple with the quark. And then longitudinally polarized component of the photon cannot couple to the quark directly. So this spin, what happens is that the spin has to flip, and then you need to have some spin polarization from the photon to flip the spin, so then this guy can still stay as a right-hand massless. This is so important that you write the structure function, you decompose into two components. I will talk about F2 and FL later. But what is more intuitive, at least at the beginning, is called FT and FL. FT means the photon transversely polarized, that part of the photon coupled with the quark. And then you can also have a longitudinally polarized photon, which does not couple with the quark. You can write the structure function in general in two terms. Okay. Now then you ask the questions, why do we even need to care about FL at all? Right? Because you cannot couple with the quark directly, but you can through a little trick. So now your photon comes in, you can have a diagram looks like this. Okay, this is called photon-gluon fusion. Okay, so with this, you can actually make sure that nothing is violated. So then not only this guy will couple, but also the longitudinally polarized photon can also couple in this diagram. So in other words, the longitudinally polarized photon, so-called the FL, is sensitive to gluons. And that's the reason why we study structure function F2 and FL. The FL is where you are trying to understand the gluon densities. And this is exactly why, because to the leading order, you cannot couple with quark with the longitudinal polarized component. So Of course, people were trying to make this easier for the measurements. So I'm going to erase here. So they can rewrite all of this equation, which is their FT, FL, their F1, their F2. There are a lot of F. So you can say the transverse structure functions 2x F1 FL equals to F2 minus 1. So now you can actually write your cross-section. Basically, I skip a few steps, okay? I think Fred actually showed this, or actually we showed this many times. Is to write a combination of F2 and FL. So the F2 and F2 actually has both the transverse and the longitudinal component. And then the FL is just isolating the longitudinal polarization component. Okay? So this is actually how we write the structural function. And I want you to remember the structural function. In fact, you can write it differently. You don't have to write it F2 or FL. You can write it FTFL. The reason, the fundamental reason is that how photon couple with quark. So now, if you stick with this, of course, this is so-called the Rosenbluth relation. Right? I think Bern actually showed it yesterday. Is that you can write this as a relation, and you use this as your variable, y, only one variable as your y-axis. Let's say this is the y squared over 1 plus 1 minus square. This is the variable. So then when this equals to 0, the intercept is F2. And then the slope is the FL. Okay? And then for a given x and q squared. So now everything is a full circle now. Okay? What I mean full circle is that you measure F2 and you measure this relation at a fixed x and q squared. Look at this. When you fix x and q squared, the only thing can change is the center of mass energy and y. So how can you change this on this slope with a fixed x and y, x and q squared? Only is a variable of y. So how can you change y? The only way you can change is by going through different energy. So the FL is trying to measure the gluon, sensitive to the gluon density. And the only way to do it, or the popular way of doing it, is to changing your energy. It makes sense because when you're going down to lower x, higher energy, you're more sensitive to gluons. And this is quantitatively how you go down to gluon is by, for example, looking at the FL, the longitudinal structure function in the DIS. And the reason I keep repeating myself, the longitudinal component, is because you can actually couple with gluon using photon-gluon fusion. Any questions? Okay, I guess not. So this is actually, I didn't write all the formula. So this is the inclusive cross-section for DIS. There are many factors, kinematic factors, the Y as the inelasticities or the energies of the photons. And then you can also make the reduced cross-sections. And then, of course, this is the separation or the relation. And then you can have a reduced cross-section as a function of this variable at the fixed x and q squared. And you can measure this linear relation. And then the intercept is F2, and then the slope is FL. Okay, so this is very important for inclusive DIS measurements. And let's take a look what we had done at HERA. So HERA, this was one of the measurements that we wanted to improve at the EIC. The reason is we only have a few energy points, right? So you see that EP is 920, 820, a few energy points. So you don't have the level arm to vary this variable at a fixed x and q squared. And that is the reason the FL is much poorly measured or constrained than the F2. because you have to vary different energy scales, energy of the collisions to vary. And this is the Hera at some Q square, some X bins, and you see that this relation was measured, and you see that for low X, the level arm is a tiny little bit because the energy range that you're changing, it's very small. And this is the reason why we adopt, most of the reason we adopt this convention using F2, and FL is because you can actually make use of it. So now the key structure function, this is a plot that we usually like to show from Rutherford scattering all the way to Hofstadter, slag, and then to CERN to Hera, which is as a function of year. Technology improves, the energy is higher, you're going deeper to the proton, and you're seeing different structure function. So this is where the initial measurements where you have the Birkin scaling, right? So you measure the F2, and then at different X bins, you vary your resolution. So this is where Bern yesterday said very nicely, you have this point light, and then so this is so-called the Birkin scaling, that as a function of Q square, it doesn't matter how much you resolve, you always see the point light structure. So now, if you go into this earlier days DIS measurements, you kind of see some hints of this scaling violation, but it was not approved until the Hera collider, the high energy electron proton collider. You see that at high X, lower energy, long exposure time, you see the quark, valence quark structure. That is the so-called Birkin scaling. And then when you go higher, or in lower X, higher energies, shorter time scale, you start to see the fluctuation of the gluon, and then the structural function starts to show up. The gluon starts to appear. Then you see that this structure function starts to so-called the violation. Okay, and that is the presence of the. So the gluon and quark distribution in the leading order is a probability to find parton in the X and Q square phase space. Okay, and this is the F2. And as I said, I'm repeating myself that this is described by the D-Glab evolution from one scale to the other. And I think don't worry about it. There will be later lectures very systematically to go through this by other instructors. So then eventually this is what the so-called the outcome of Hera, right? That the front and center of the Hera scientific output is to have the PDF, the parton distribution function. And you see that the valence quark is at high X, and then the C quarks and gluons. And then if you actually see the scale in the linear scale at lower X, you're essentially overwhelming dominated by the gluons. The valence structure is basically invisible. Okay, so that is the foundations of the DIS and for the EIC. So for the EIC, I recall, this is the Bible of the EIC. It's the EIC white paper. And it's a really good reading. I really suggest, even when I prepare this lecture, I still go back to the EIC white paper to understand better what's about the EIC. So if you think about what EIC physics would do, this is my summary. It's usually the three pillars. It's the 3D imaging, which is very intuitive, because when you're doing DIS, you're only looking at one dimension. You also wanted to look at the three-dimensional structure of protons and nucleus. Okay, I think this cannot be more intuitive. You wanted to know what the structure inside of the proton. And then the second, not so intuitive, is the origin of mass and spin. Right? When this QCD emergent phenomenon, how do we contribute to the mass? And finally, the gluon saturation is when you accelerate a proton so fast or at a very high energy limit, the gluon keeps showing up. When does it stop? And that is related to the gluon saturation. So the first one, this one, I'll only tell you the high level, and then we'll have a dedicated lecture about imaging, is the following, so-called the 5D Wigner functions, okay? You have different momentum fraction X, you have the momentum KT of the parton, and you have the positions of the parton. So you can actually, in principle, measure the Wigner function, then you measure everything. Everything about momentum, the positions, and so on. So this is the usual thing we show, that if you from a Wigner functions, you can actually integrate out the position dependence, and then it becomes in the momentum space, then you have so-called x and kt. And this is usually what we call the TMDs, the transverse momentum dependent DPMs. And then of course, you can go to position space, going the other way around, and then you actually now get in the coordinate space, you take an image of this spatial positions, of course. So they're all coming from the modular distribution, depending on which degree of freedom that you're trying to integrate over. And of course, when you're going to even integrate out another variable, here you integrate the b, the position, here you integrate over the momentum, you're going back to the one-dimensional structure function or one-dimensional Poisson distribution, which is the PDF that Hera had measured very well. You see, this is from Hera. Okay, so you have a 5D dimensions, and you can integrate out different parts, and you can go back to the one-dimensional image. So then with the coordinate space, you can continue, and you can say, okay, let's say in a B position and the momentum of Fourier transformation, you can actually go back to form factor, right? Remember form factor. And then you can also go into a different, they call this the skewness. This is the generalized Poisson distribution, GPD. So the physics picture is so intuitive for this part, but calculating it and measuring it is so hard. Okay, it's such a big contrast. So there will be dedicated sessions about this. But remember all of these terms. You have a Wiener distribution, you have TMDs, and PDFs, and GPDs. So this will be the terms. If you stay in our field, it would dictate your life probably, most of the time. So the second one is the mass. Okay, so now this is the interesting part. Okay, it's a very challenging and very hard to understand, in fact. So the mass puzzle is that the gluon is massless, right? Gluon has no mass. Quarks, the valence quarks, the bare quarks, we know is a few MeVs. So the proton is 1 GeV, so it's about 100 times heavier. So this is one of the puzzles that in QCD, why does proton so heavy, right? If the quarks is very light. And then this is also go back to the central questions. How does this confinement, when you put quarks and gluons together into the proton, how does it bind together? And actually, this emergent phenomena provides you this effect of mass. So this mass problem is really the central at the EIC. So let me give you my intuitive way of understanding mass, okay? And this is, if you want to do it rigorously, of course, this is very complicated. So if the quarks doesn't add up to the proton mass, where can it come from, right? So naively, you can think it comes from actually the momentum, the energy inside of the proton. And also there's a very important factor is the vacuum. So this is such fascinating physics, okay? I'm doing this physics every day and I'm still get fascinated by it. It's that because the QCD vacuum is not so trivial. It actually has a lot of properties that can impact how this visible matter or this proton behaves. So for example, let me give you a very quick rundown. Is that quantum mechanics, actually, last year we celebrated 100 years of quantum mechanics, is the uncertainty principles, right? You have uncertainty principles, meaning that you can borrow some energy if you return it back quickly, right? So you can violate something if you do it quickly. It's like, who drives a menu shift, sticker shift car? Who knows how to drive? You? Okay, so when you drive the manual car, you have to, both hands needs to be used. What if now you want to have a coffee? You want to take a coffee. All of a sudden you need 3 hands. But now here's the trick. If you do it quick enough, hands doesn't have to be conserved, right? You can do it quickly and then shift gear. Exactly what happens. If you do it quick enough, energy doesn't have to be conserved. This is uncertainty principle. Okay? So now vacuum, it's a such bizarre state, or it's a normal state we just didn't understand, is that you can have this so-called zero mode, 0 point energy. Okay, that you can have a 0 on average but you have some fluctuations in the vacuum. Meaning that the vacuum is like this kids. It cannot sit still. It has to fluctuate. So it can fluctuate up and down with different energies in the vacuum. And this is so-called a vacuum fluctuation. So we have the QED, we have the QCD. This is probably the entire course that you can take in your class. But fast forward is that there's a special, or is a consequence of QCD vacuum, is that you have a so-called chiral condensate. Remember chiral condensate? Have you taken this class? Chiral symmetry breaking. So you have this so-called QQ bar in the vacuum that is not zero. The expectation value of this quark-antiquark pair is not. Okay. And this is actually so fundamental to QCD that impacts everything we interact. For example, the proton has to be inside of the vacuum. You cannot be out of the vacuum, right? It's always impacted by the chiral symmetry breaking. So if you're talking about a high level conclusion is that the proton mass has a very deep connections to the vacuum structure, to this chiral symmetry break. So one thing that is I want you to have a picture is that this density is about 250 MeV to the cube. Remember the pocket formula about 200 MeV, 1 Fermi? This is the scale, right? So actually, if you translate this, it's about 1 to 2 pairs of QQ bar per Fermi cube. This is very, very specific, right? In a 1 Fermi cube of space, you actually have this quark condensates about 1 to 2 pairs. Okay? So this is like a medium in the vacuum that you actually fill up the entire of our space. So with this, that you can say, okay, chiral symmetry is breaking in the vacuum, and you should go back to the textbook about the chiral symmetry breaking. I'm just gonna tell you how this naively or intuitively, how mass can arise. So now you can write the quark in terms of, let's say I have a right-handed quark. I have a right-handed anti-quark as in the condensate. So now I'm shooting a quark which is massless. Okay, in the massless limit, I have a quark of right-handed quark going through the medium, the condensate. So the right-handed quark and right-handed anti-quark will annihilate because they go back to the vacuum. And then what comes out is that the left-handed quark. This is amazing, right? You shoot a massless quark, right-handed, it annihilates with the interact with the medium, which is the vacuum itself, and it comes out as a left-handed quark. So as an observer, so if I am this dummy looking at this process, and you say, helicity flipped or chirality flipped. So remember, I keep saying this concept. What does helicity flip means? Yeah, but when it flips, what does it imply? I keep saying this massless limit that chirality is conserved, strictly conserved. So the fact that this is not conserved, it means the consequence is it has mass. So the consequence of this interaction is the dynamical way of generating mass. So think about this. If the proton has no mass, but the proton has 3 quarks or many quarks, there's no rest mass. But because the interaction with the condensate, you can actually effectively call the dynamical generation of the hadron. Okay. So this is something I think I want you to remember, that the proton mass is a consequence of this QCD emergent phenomenon. It's interacting with the vacuum. Okay. So I have other things, but I think I'm really running out of the time. Of course, in recent history, that actually people in QCD, they can so-called the mass decompositions. So you can actually decompose into different components where the mass coming from the quarks, the bare quark mass, or the kinetic energies of quarks, the gluons, and so on. And there's even one more very mysterious contribution. It's called the trace anomalies. Okay, I'm not going to talk about it, but this is something that also contributes. This is very unique to QCD. Okay. So here is I only have one line, okay? I was kind of lazy to make slides, but this is basically in Xiangdongji in 95. He actually proposed the first time how to decompose into different terms. So basically this dynamical generation of mass is kind of a few combination of these terms, right? How does quarks interact with the vacuums? And this is actually effectively the contribute to the proton. But the things I want you to remember is this picture is that this dynamical generation of mass has a very deep connection to the QCD vacuum. So right now, I want to advertise my own work, okay? Since I have the floor. Recently, our group actually discovered a way to probe the vacuum condensate, okay? So this was featured by the cover of Scientific American, also on Nature. So the idea is the following. So now you have a quark condensate, and then actually the quark, an anti-quark needs to satisfy the vacuum quantum number. So the vacuum quantum number JPC equals to 0 plus plus. I hope everybody knows this because the vacuum should be rotationally invariant. You don't have any total angular momentum. And then the parity needs to be positive. It has to do with the angular momentum. And then if you look at this, L equals to S. This has to be positive. This has to be 1. This has to be 0. So in other words, there's only one unique solution that the quark, anti-quark pair in the condensate has to be spin 1. The two quarks has to be aligned. So by using these concepts that we can actually trace this back to the vacuum through so-called the lambda polarizations. And if you're interested, you can read the paper, okay? All right, spin. How do we understand spin? This is also very fun because naively, you say, okay, spin should be the spin of the quarks. Can I erase it? Probably. So if you think about in the quark model, the spin of the proton in a okay, I'm not going to write 18 terms. Don't worry, okay? All the permutations. So you can say, okay, there are 3 quarks. They're UUD, and you can just assign spins, and you can get all the combinations to satisfy, right? This is the quark model. So that was naively what people believed at the time. If you have a spin 1/2 of your proton, somehow these 3 quarks should rearrange in a way that contribute to the spin of the proton. That was the assumptions. But then, of course, in the 80s, this famous experiment, CMC, measured that quark almost carries 0 spin. Okay. So that was so-called the proton spin puzzles. So where does the spin come from in the proton? So this is a modern language that we can decompose into spin of the quarks, spin of the gluons, orbital angular momentum of quarks and gluons. So one important thing here is that I wanted to show you how this experiment was done. Okay, this is very important. So now you think about you have a proton, you have quarks, many quarks. So one way to tell how does the spin of the quarks contribute to the proton is that you can now polarize your proton this way. This is your proton polarization. And then you check whether the quarks also polarize, align with it, or you polarize your proton the same way, whether your quarks anti-align with your proton spin, right? If the quark spin does not contribute to the proton, when you going this way or going this way, it will not affect the quark spin inside of the proton. That is the fundamental idea, okay? So I think this is one of the most beautiful experiments ever. So now, think about it in this case. Now we have a photon comes in, DIS, right? Photon DIS. And then now you have a quark going this way. They're always colliding in this way, so their momentum is always opposite, okay? And then now I can have my, remember the photon polarization, transversely polarization, you can have spin. And then now you have the quark spin going this way, okay? Going this way. So you can also have 4 combinations. So the photon is spin on that way, and the proton going this way. Okay. So now, first remember, quarks can only couple with the transversely polarized photon. The reason is if the photon is longitudinally polarized, the SZ equals the 0 component cannot couple with quark because of the helicity wants to stay. So now you can have the photon, after you polarize it, it can be going this way or going that way. So you have 4 combinations. Okay. So now this is before your collisions. The first one, after this, the quark, let's say, go backwards. The momentum goes this way. Helicity wants to stay, correct? Massless quark. So the spin has to go back this way. So can the spin go this way? The photon provides the spin, right? The spin 1. So this is called, spin is +1. This spin is -1/2. So you do the math. Here, this plus this, the SZ equals to +1/2, which is allowed. Helicity is a right-handed particle, goes to right-handed particle. This is perfectly allowed. Okay. This is good. Okay, how about the second one? Now the second one, SZ equals to -1. This is SZ equals to -1/2. You immediately see the problem. This plus this is -3/2. Quark cannot carry 3/2, right? So now the quark goes this way, and then the spin actually also needs to go to this way. There's no way the photon can provide the spin to flip this guy, right? This guy not suppressed. In the extreme case, forbidden. All right, the third case, I want some of you to try. Right? So what should I write? What's the photon spin? +1 going this way, and this guy +1/2, right? So the helicity is what? Left-handed, right? Opposite spin. So now the quark goes this way, and it wants to, this is the only allowed state. It wants to be a left-handed, but the 2 spin add up is 3/2 this way. Right? So not allowed. Final one. Okay. So -1. So this can be goes this way, and it wants to be spin this way to stay as left-handed. So this is SZ -1/2. So this is allowed. Exactly. Good observation. So the spin, if it's the opposite direction, it works. If it's the same direction, it doesn't. So now it comes in. Now, if I wanted to flip the spin of the proton, right? So I I have one side, the photon stays the same. So let's say I have these two diagrams. So the photon 1 and 3, okay, look at 1 and 3. So that means my photon stays the same. My electron beam stays the same. I flip my proton beam polarization. So if the quark follows the proton spin, that means when my proton polarizes this way or this way, my quark is going to follow. Then is one, which is helicity. This is called plus plus, minus plus, plus minus, minus minus. So that means 1 and 3 is that plus plus should be allowed, plus minus not allowed, should be greater than 0. It should not be equals. This is where the asymmetry comes. Okay, because the quark wants to align with the proton spin. So you polarize the proton this way, and you say, okay, quark all aligns, and you polarize this way, quark all aligns this way, and then you compare the cross section between these two, and apparently, if it follows, this guy should be not allowed, right? So that's how you make the measurement. This is the EMC effect. Not the EMC effect, the EMC experiments to measure the proton spin. Okay? I think it's one of the most beautiful experiments. It's so simple. Helicity argument. You have absolutely no idea how they interact inside the proton, but it doesn't matter. Using this way, you can compare these two. Okay? Any questions? And I keep saying about this polarization and helicity. You see that in high energy scattering, this is so fundamental. Almost everything is connecting to this concept. So we usually call this the A1 xq squared equals to or approximately this ALL, or A parallel, for D, which is so the G1 is so-called a spin-dependent structure function. And that is coming out of this asymmetry measurements that you wanted to, actually, let me write it out. Okay, so it's just a symmetry measurement. You flip the beam and you count how much symmetry you have. And this is related to the G1 structure function. So I really run out of time. So I will tell you. So this was the original measurements of the EMC. You can check in the late 80s. And you see that it's A1P, the proton. The first thing you observe is not zero. Okay, so it's not zero. But then you trying to understand this in details, how you're gonna fit into this G1. And then they actually found out about the quarks doesn't carry as much spin as you think. So there are so many experiments over the years to build up. So eventually Hermes is one of these fixed target experiments in Hera, actually use different tagging methods to confirm that quark spin is about 30%. This is more precise. So originally they think about this as 0%, which is too extreme. But then the modern number is that the spin of the quarks is about 30%. So the rest have to be 70%, something like that. Okay. So your homework, okay, your homework is to see how does STAR, my very proud experiments, discover that gluon also carries spin. Okay, so this is one of the things that you should go back and think about how this is very similar measurement. It's also an asymmetry ALL as a function of jet PT. And our discovery was that we showed the gluon contribution to the spin of the proton is also non-zero. And this is something. Okay, so maybe I'll stop here for today, and then I'll continue with the saturation and some measurement tomorrow. So thank you.
Thank you, Conrad. Questions or comments? homework.
Maybe I should ask somebody to explain to me how EMC measure quarks. Anybody wants to volunteer? Oh, come on. Go ahead.
So, after some of the pioneering experiments at SLAC, they measure A1 down to very small x, which you can then convert to G1. You integrate over G1 over x, then you can compare it against the LSEFE sum rule, which you can then decompose into the various contributions. And I did have a comment that the EIC is extremely interesting for those of us who study double spin asymmetries because no one's ever done polarized beams for both lepton and nucleon. So you can access a different part of the phase space that doesn't exist for A1.
Thank you for the comment. And I mean, the obvious extension in kinematics because the collider kinematics. Right? Usually we do this in the fixed target experiments. You polarize the beam and polarize target, but then the phase space, of course, is not as wide open as in DIS. So in the electron-ion collider, you can polarize both beams, hadron beams and the electron beams. And then you can, of course, access spin-dependent structure functions to a very complex. Very good comment. That is the part that I wrote it down here. I didn't have time to say, which is you can look it up. More important part is how this measurements.
We are running out of time, of course, but I think your measurements of lambda polarization are very interesting. Can you say maybe just a few words
But
how the lambda polarization?
I did not pay him to ask me this question. So the idea is that in the PP collisions, something happens here. And what we see is that there's a lambda particle, there's an anti-lambda particle, pair produced, lambda, anti-lambda. So lambda is UDS. If you don't know, you should know this. And then lambda bar is UDS bar, right? So it contains an S and an S bar. So in the very naive quark model, which is, some people said is not right, but then for this case, it's actually quite applicable, is that if you write down the same equation as proton for lambda, this becomes very simple because UD is a spin singlet. S actually becomes the spin of the lambda. So if you measure lambda, you essentially measure the spin of the strange quark. So this becomes much simpler. And then the lambda would decay into proton-pion pairs. And then because of the weak decay, the momentum information of the proton carries the spin. So now if I have a pair, I can boost them into their center of mass frame and compare their spin direction between the two lambdas. So I can check whether they are in a spin singlet state, which is like this, or they are in a triplet state, right? There are three terms here. So basically, by measuring these lambda polarizations, we actually confirm that this is actually a spin triplet state, and also the magnitude of this polarization is at its maximum. And one of the only reasons I think that it can be such a large spin correlation is because of the vacuum polarization.